Welcome back. Today, we are diving deep into what is, I think, one of the greatest technological marvels of our time, the microchip. I mean, it powers literally everything in our modern lives, but how it's actually made, well, that's a process that borders on science fiction.
Just take a look at this. You might think you're looking at an aerial photo of some massive, futuristic city. And you're not wrong, in a way. This is a microchip, a dense, incredibly complex metropolis with billions, literally billions, of inhabitants called transistors, all crammed into a space smaller than your fingernail.
So that's really the big question we're tackling today. How on earth do we build these microscopic cities with such unbelievable atom-by-atom precision? Let's get into it.
Okay, so the most fundamental building block of this whole city is the transistor. It's just a tiny little switch. But here's the catch. The material it's made from, silicon, isn't that useful in its pure form. It needs a secret ingredient to work its magic.
And that secret is a process called doping. In the world of chip making, this means we're intentionally adding tiny, super specific amounts of other elements, what they call impurities, right into the silicon crystal. This is the magic trick. This is what allows silicon to be switched on and off, creating the ones and zeros that are the foundation of all digital information.
So let's zoom in. Here's a cross-section of just one of those billions of transistors. The real challenge, the core of the whole manufacturing process, is creating these tiny, perfectly doped regions you see layered in there. Getting that recipe exactly right, well, that's everything. So, how do they do it? Well, for decades, the go-to method was a process called diffusion. You can think of it as the original, kind of brute force, but actually very clever way to get those impurities into the silicon.
The best analogy is honestly baking. You literally put these silicon wafers into a super hot furnace, anywhere from 1,000 to 1,300 degrees Celsius, and you let a gas containing those impurity atoms just soak into the surface. They would slowly diffuse into the silicon.
But you can imagine, just baking something isn't super precise. So engineers came up with this really brilliant two-stage process to get more control. First, they do something called the drive-in, a quick, short bake to create a really thin, highly concentrated layer right at the surface. Then that was followed by the drive-out, a longer bake at an even higher temperature to push those impurities deeper into the silicon to the exact depth they needed.
And this graph shows you exactly what happens. First, look at curve 1. See how steep that is? That's the drive-in, a huge concentration of impurities right there at the surface. Then, curve 2. That's what happens after the drive-out bake. The impurities get pushed deeper, and the concentration kind of spreads out more evenly. It was a remarkably effective way to control what was happening.
But as transistors got smaller and smaller and smaller, even this clever baking method just couldn't keep up. It hit its limits. The industry didn't need a furnace anymore, it needed a scalpel. And that brings us to the modern technique, ion implantation.
This table lays out the differences perfectly. You've got diffusion, the high-temp baking method, versus ion implantation, which is more like atomic billiards. It gives you way higher precision, works at lower temperatures, but, and this is a big but, look at that bottom row. It causes a lot more damage to the silicon crystal.
The atomic billiards analogy is the best way to think about this. You're basically using a small particle accelerator to fire individual impurity ions at the silicon wafer with an incredible amount of energy. So instead of gently soaking the surface, you are literally shooting atoms into the silicon to place them exactly where you want them to go.
And the result? It's just staggering. Look at this graph. Remember that smooth, sloping curve from diffusion we just saw? Forget about it. Ion implantation creates these sharp, incredibly well-defined peaks of concentration at very, very specific depths. I mean, this is atomic-level control. It's wild. But all that precision comes at a price. Firing atoms into a perfect crystal structure is, a pretty violent process. It shatters that beautiful lattice, creating this damaged, amorphous layer. So you have to add another crucial step called annealing, which is basically a quick, high-temperature flash bake to heal the crystal damage and get those new ions to settle in and become electrically active.
Okay, so let's zoom back out for a second. We've been deep in the trenches talking about these incredibly precise methods for building transistors, literally atom by atom. Why does all this nanoscale engineering matter on a global scale? It matters because this right here, this relentless innovation is the engine that has been powering Moore's Law for over 50 years. You know, the famous observation that the number of transistors we can cram onto a chip doubles roughly every 2 years. This is the exponential curve that gave us everything from our smartphones to modern medicine.
But this progress has created this absolutely mind-bending economic paradox. You can see it right here on this graph. That green line, using the axis on the right, shows the cost of a single transistor just plummeting over time. That's why our gadgets get cheaper and more powerful. But at the exact same time, that blue line, using the axis on the left, that's the cost to build a factory or a fab to make these things, and it is skyrocketing into the billions.
Yep, that's not a typo. We're talking more than $10 billion for one factory. It has become a technological arms race, where the weapons are billion-dollar clean rooms and machines so complex they're almost unimaginable. The cost to even play the game is just immense.
And here is the final twist. You know all those nanometer labels we hear about in the news? 10 nanometer, 7 nanometer, 5 nanometer? Well, it turns out they aren't actually a literal measurement of anything specific on the chip anymore. As one industry forum finally admitted, at this point, it's basically just a marketing term. It's a label for a new generation, not a physical dimension. So that's where we'll end it. We have achieved a level of mastery over the physical world that is just astonishing. We can command individual atoms to build the brains of our entire civilization. But now, as we push right up against the fundamental limits of both physics and economics, the real question becomes, what impossible art comes next?